a connected subspace of a topological space cannot lie across a separation. So we have an important theorem. Let X be a topological space. Suppose that A and B form a separation of X. In the previous sessions, we defined what a separation of a topological space is. So in this case, we are having A and B forming a separation of X. C is a connected subspace of a topological space X. Then either this connected subspace of X, it either lies in A or B. It cannot lie in their intersection. So in simple terms, we are going to say that a connected subspace of a topological space cannot lie across a separation. In terms of a pictorial, we have a topological space X. Then we have A and B forming a separation of X. So this is my A. Also, this is my B. We defined what it means for two sets to form a separation of a topological space. So this is X in simple terms. This is our topological space X. So we have C being a connected subspace of X. So C is a connected subspace of X, and if that C is connected, then it must lie either here, it must lie entirely in A, or it must lie entirely in B. It cannot lie across a separation. We cannot have a connected subspace C of X lying across a separation. No, it will either be in one of the set or the other. So how can we demonstrate this? So we are going to let the proof of this. We are going to let A and B be open sets. They are open sets in X. Be open sets in X, such that A and B are non-empty. They are distinct, non-empty, distinct, and they are also disjoint. Let them be open sets which are non-empty, distinct, and disjoint. Then we can write X as A union B. X as A union B. A and B form a separation of X. Now, since C is a connected subspace of X, since C is a subspace, since C is a subspace of X, then A intersection C, B intersection C are open. They are open sets. They are open sets in C. We define a subspace topology. Open sets are always in a subspace topology. Open sets are always this set intersection what is open in the mother topology. So these and these are open sets in C. Moreover, the open sets in C. Moreover, in fact, let me say they are open sets in C since A and B, are open sets in X. Moreover, what do we have? Moreover, A intersection C intersection B intersection C. This is the same as A intersection B intersection C, which is an empty set intersection C, and this is equal to an empty set. So these two open sets in C, they are disjoint. Also let us compute their union. A intersection C union B intersection C. This is equal to A intersection B union C. A intersection B, is that thing correct? We have to first scrutinize it and convince ourselves that actually this is correct. Is it correct? No, it's not correct. So this is A union B. This is A union B intersection C. Yeah. So this is A intersection C union B intersection C. Yeah. And A union B, this is X intersection C. X intersection C, that is C. So you realize that these two open sets, they are disjoint. And they are disjoint since the intersection is empty and their union is C, and they form a separation of C. So from I can call this 1 and I can also call this 2. So 2 and 1 imply that A intersection C and B intersection C form a separation. They form a separation of C. They form a separation of C. A intersection form a separation. They form a separation of C. They form a separation of C. So this is a contradiction. This is contradiction. This simply means contradiction. Contradiction to the fact that it's contradicting the fact that C is connected. That is the contradiction of the fact that C is connected. So what do we have? So we have these two open sets in C, which are disjoint, and their union is C. So they are separating C, but we know that C is connected. Now, since C is connected, we cannot have these two sets. We cannot have these two open sets forming a separation of C. So this implies that one of the sets, we have this set and this one. So one of them must exist while the other shouldn't exist. This is what I mean. One set should be empty and the other one should be non-empty. So this implies that not both A intersection C and B intersection C are non-empty. Not both of them are non-empty. So this implies that either A intersection C is an empty set or B intersection C is an empty set. What does this imply? Either A intersection B is an empty set. We cannot have both of them as empty sets. So either A intersection B is an empty set or B intersection C is an empty set. So let us assume, without loss of generality, so suppose that A intersection C is not both of them are non-empty. Yeah. So this is not both of those empty sets are non-empty. So one is empty or the other is not empty. So either this is empty or this is empty. But you cannot have both of them as empty sets. So suppose that A intersection C is empty and B intersection C is non-empty. What does this imply? This implies that this implies that C, which was actually A intersection C union B intersection C. Now this is equal to an empty set. This is an empty set union B intersection C. So this is equal to B intersection C. So C is B intersection C. What does this imply? This implies that since C is the intersection of B and C, this implies that C is a subset of B. The subset of B. Similarly, suppose that A intersection B is non-empty